Okay, I think we are ready to continue with stochastic integration. That's a very good topic. Okay, we continue with stochastic integration. Stochastic integration. We will try to solve as much problem as possible to minimize the number of theorems and definitions, but that's a very tough subject. That's very mathematically intensive subject. And the first problem that all the rules of integration work. All the rules of integration do not work. That's the main problem. So, last time we have discussed the integral from, let's say, 0 to t 1 times dw, and we have also discussed the integral from 0 to t wu times dwu. Yeah? The first one is very intuitive. Once again, I remind that we interpret two functions. We look and we see not one function, but two functions. We see here the quantity function, and we see here the price function, the price function. And to integrate, we interpret this integral as net profit of trading strategy, of specified trading strategy. So basically, in this example, I have two functions. Again, I attention that we start our investment game at time 0. We finish our investment game at time t. The quantity, we have one share or one apple. Yeah, we have before. Yeah, maybe I will choose another color to show the difference. Before we have 0, we have one share here. Yeah, we have one share here. We have 0 share after our time 10, and the price is random. Price one, I can plot some trajectories. Yeah, this is time, this is of t, and the price is winner process. Yeah, it looks something like this. Yeah, I may draw. So that's some trajectories, but we should understand that in this example, quantity function is deterministic. There are nothing random, and the price function is stochastic. And to integrate that easy, we just say that if we have one share, we should buy it. We buy one share at price W0. So we buy at equal to 0, and we sell this share at time t. We sell the share at time t. And hence, that's our net profit. In this particular simple case, it is consistent with all the formulas. We integrate this guy, we get exactly the old result. So that's coincides with Newton-Lewis formula. Leibniz formula from high school. Yeah, probably you remember the formula from high school. But as we have shown a week ago, we have shown that integral from 0 to t wu dwu. So that was a week ago. Yeah, a week ago. It was tough, but we managed to show using limits. We managed to show that it is wt squared minus t of 2, and this result does not coincide with Newton Leibniz formula. And we needed to understand well properties of stochastic integrals. So let's discuss some general results, because if we will always take limits, then it will be tough. Normally you calculate integrals using limit. You know some rules. Yeah, you know that integral of x. So you have some rules. And integral from 0 to let's say t x n dx is t n plus 1 over n plus 1. So you have some rule, but normally you never calculate limits because it's a very long process to divide the interval of time into n small segments, calculate some, replace the sum by the limit, and so on. So we basically have some rules, and we not calculate integrals using limits. So let's do the same thing. We will describe the properties of stochastic integrals. Okay, let's move on to the properties of stochastic integrals. First, let's discuss shorthand notation. Shorthand notation. In mathematics, we rarely use shorthand notation. Normally, we prefer to be rigorous. So we prefer to say if A is equal to B, we mean that A is equal to B. Normally, when we write that A equal to B, A is equal to B, that really means A and B are the same. Yeah, but sometimes this agreement is violated. Yeah, there are some convenient examples where it's better to violate implicit agreement. Yeah, so normally when we write quality, we mean that the same. Yeah, the same objects, the same objects, the same object. Yeah. But there are some exceptions. There are some exceptions. For example, if we write x cube is equal to small o of x, that's correct. If we write x is small o of x, that's also correct. Yeah, but that doesn't mean that x cube is equal to x squared. Yeah, we write this, but this is not a usual equality. That's just an agreement. Just a gentleman's agreement. We say that when we write, so that an agreement. Yeah, to simplify exposition, that's agreement. When we write f of x is equal to small o of x, really means means something different. We say that, that's an agreement. When we write x cube is equal to small o of x, this really means that limit when x tends to 0, x cubed divided over x is 0. Yeah, basically that means that x cube decays faster than x when x tends to 0. But we are lazy to write this limit every time, and we prefer shorthand notation. Yeah, we should be clear that we write equality, but we do not mean that x cubed and x squared are the same objects. Yeah? It's just an agreement. Yeah, and just an agreement. Okay, that's clear. Yeah, that when we write x cubed is equal to small o of x and x squared is equal to small o of x, we don't really mean that it's the same object. That's agreement to simplify, to avoid writing limit every time, limit. So instead of this, we just use this shorthand notation. That's okay? Any questions? Anyone? Are you alive? Okay. Is it clear? Any questions?
Yep, that's fine.
Okay. And in stochastic calculus, we have also an agreement. Agreement in stochastic calculus. We have also agreement in stochastic calculus. Stochastic calculus. We write dxt is equal to at dwt plus bt dt. We write this. We write this, and we mean that xt is equal to x0 plus integral from 0 to t au dwu plus integral from 0 to t bu du. So that's also an agreement. We write short formula and we mean long formula. Why? That's an agreement. X is a rigorous, well-defined mathematical object. Xt is a well-defined mathematical object. To be more precise, xt is a random variable. To be more precise, xt is a random variable. We can calculate expected value of xt. We can calculate weights of xt. We can calculate probability that xt is bigger than 42, and so on. That's a real random variable. Sometimes it's tough to study it, but it's a real honest random variable with distribution, with probability density function, probability distribution function, with expected, with variance, with anything else. And dxt does not exist. Yeah, careful. dxt does not exist. That's not a random variable. It's not a random variable. It's not a random variable. That's not constant. It's not constant. Yeah, that's just a short way. So we just save ink and space. We just save ink and space. Yeah, instead of form, instead of full form, use short form. is short form. And that's probably this notation will speed up our expression, but you should understand well from the beginning that once again, dxt, dwt, they do not exist. They are not well-defined mathematical objects. We can't calculate the variance, the expected value. That's just a shorthand notation. Okay, continue with a small table. We write, we mean. We mean. And we write that dxt is equal to at dwt plus e dt. We really mean, once again, xt is equal to x0 plus integral from 0 to t au dwu plus integral from 0 to t bu du. Okay, for example, yeah, if I write dxt is equal to wt, I really mean that xt is equal to x0 plus integral from 0 to t xu dwu. So okay, that's a shorthand notation. We should always understand that dwt does not exist. But the problem that this shorthand notation is very powerful. Yeah, it's very often used in mathematical finance, and if you first encounter, it seems like some kind of nonsense. When we write expected value of I don't know, of at dwt, we really mean expected value of integral from 0 to t au dw. So when we write this, we mean this. So once again, that's a big problem. You encounter this notation every time. You see in some books something like expected value of dwt is 0. dwt, one thing, does not exist. Yeah, it's not a random variable. Just a short way to write long statements with integrals. So once again, dwt is not a random variable. So expected value of wt is meaningless. But when we write, so that's okay, in many good books, this formula, and that's completely fine. That's just a tradition. Author really means that expected value of integral from 0 to t 1 times dwu is equal to 0. So when we encounter expected value of dw, we really mean expected value of the integral. Even more. So that's the problem. In stochastic calculus, we have a shorthand notation that is very popular because it saves a lot of time. But when you start to study, you may be fooled by some expected value of non-existing object. And when you start to study stochastic calculus, you should always ask yourself, okay, this thing, is it a real thing that's a random, or is it just a shorthand notation about some statement that is long to write? Yeah, that's very important. For example, the same applies to variance. You may encounter something, variance of A T D W T, we really mean, when we write this thing, we really mean of integral from 0 to t a u d w u. So we really mean this. Yeah. Once again, a t d w t doesn't make sense per se, and doesn't make sense. That's not a honest mathematical logic. For example, you may encounter in text something like variance of dwt is equal to t. What does this really mean? It really means that variance of integral from 0 to t 1 times dwu is equal to integral from 0 to t 1 times du. And that's the first problem. We should always distinguish honest, rigorous mathematical notation from shorthand notation that has no meaning itself, but that's just a way to write quickly some true statement. Yeah, that's clear. Yeah, that's okay. Any questions here?
Sorry, what is AT and BT?
Some AT and BT, and there are some random processes. So AT, BT, XT, WT are stochastic processes. Stochastic process. WT is the winner process. These are honest mathematical objects. You may calculate, so if you are given some more information, yeah, if you're given some more information, you can calculate the expected value, the variance, probabilities related to them, okay? That's fine.
Okay, and what is the difference between stochastic process and Wiener process?
Stochastic process is a general concept. The Wiener process is a particular case of stochastic process. For example, you consider AT that's just WT squared. WT is a Wiener process. And AT is not a Wiener process. It's not Wiener process. So Wiener process is a particular example of stochastic process with 5 properties. It should start at 0. Yeah. It should delta WT minus WS should be normally distributed with mean 0 and variance T minus S if T is bigger than S, and some other properties. And A is just a stochastic process. It may have, for example, WT may go below 0. So if the trajectory of WT, it always starts at 0, and it may be below 0, but if you draw the trajectory of AT, so it will never be, never below 7, yeah? That's okay?
Yes, thank you. And what is the intuition for this shorthand notation? For example, first shorthand notation that is written outside of table, why can we mean such thing based on our notation? I'm talking right now about a first example that is not in a table, I assume. Well, it's actually in table as well. Okay.
Which example do you mean? I have a big
Like
table.
the first one. The first one.
DXT, this one.
Yes. Well, I understand that DXT is not existent as it should be, but how can we go from like notation on the left to notation on the right?
The gentleman's agreement. We agree to agree. Мы говорим партия, подразумеваем Ленин. Говорим Ленин, говорим. That's agreement. That's a notation. Why some function is noted cost? Well, that's an agreement. We agree to
Okay.
denote this.
And
When
what is
so
okay, sorry.
maybe in some other world the agreement is so why the cat is called cat, why it's not meow meow, and it's called it's an agreement. We agreed to cat. That's an agreement. We agree to sum of integrals. We agree to write like this. The reason for agreement, agreement saves space and time. So you see, you don't need to write integrals. So it saves time.
What is the sense of this expression like dxt is equal to at dwt plus bt dt? Well, I can see the mathematical expression to the right that explains it, but I look at it and I feel lost.
Okay, let's go back to ordinary calculus. Okay, let's back to ordinary calculus. Let's go back to so first point. That's an agreement. We agreed to write this dxt for, we really mean this sum of two integrals plus a constant. Yeah, this guy is constant, and we have integrals more. So let's go back to calculus.
Yes, just could you please again remind what is the economic intuition of these integrals, these stochastic integrals?
Let's go. That's important to understand. If we have integral from, okay, let's solve one more example, because if you are lost here, then we can't continue. Example, once again, the meaning of the stochastic integral. Imagine that we integrate from 0 to t, au dwu, and our function au is equal to, it's 1 if u changes from 0 to, let's say, 2, and it's 5 when u is from 2 to plus infinity. Okay, we interpret this function as the quantity. How many shares do you have? That's your trading strategy. How many shares do you have at home? Yeah, how many do you have at home? And this is, so you basically decide how many apples, and you decided that from moment 0, up to moment 2, you will have one apple at home. At time moment 2, you will go to the store and will buy 4 apples more, in such a way to have in total 5 apples at home. Okay, that's quantity. AT. Yeah, that's okay.
Yeah, it's perfectly fine. And U is price
of an apple or share.
And the integral resembles like our product after this period, right?
We close the deal. For example, let's calculate this integral. So basically, we see two cases. If t is lower than 2, if t than 2, then basically we buy one apple and we sell one apple. So we buy one apple at time 0 and we sell one apple at time t, if t is equal to, if t is less than 2. But t is bigger or equal than 2, yeah. If t is bigger or equal to 2, then initial moment of time we buy our portfolio, we buy one apple at price 0. At time moment 2, we buy 4 apples more. Yeah, we need to buy 4 apples more. And here we buy plus 4 apples. Yeah. We buy 4 apples more, so time moment 2, we pay minus 4 times W2. And when we close the deal, T, we sell our portfolio. At home, we have 5 apples. So if we sell our portfolio, it will bring us 5 times WT dollars. Yeah, that's okay?
Okay, thank you. I got it now. I just needed to remind myself that it is equal to net profit.
Yeah, that's a net profit. Yeah. And W has some properties, so we can simplify these expressions, calculate expected value, and so on. For example, W0 is 0, and so on. So we have some information, so we can simplify this. But that's the main idea. Yeah. Okay. So now, why? So probably your question is why we are interested in such ugly processes. Yeah. Why we are interested in such ugly processes, why we may be interested to write them so often that we need special shorthand notation. Yeah, if we invent shorthand notation, that means that we'd like to write this sum of two integrals and the constant very often. Yeah, why we need shorthand notation? Because without shorthand notation, we will write the sum of two integrals very often, and we will spend a lot of time. Yeah. Okay. So the question probably, why on earth will I write these sum of two integrals too many times to invent shorthand notation? Yeah. Probably the question is why need shorthand notation for such strange object? Yeah. I encounter this object for the first time. I can write it without shorthand notation once in my life. Yeah. But the problem is that many stochastic processes can be represented in this form. So the reason, so question, probably I will rephrase the question, why we need shorthand notation for for x0 plus integral from 0 to t a u d w plus integral 0 to t b u d u. And the answer is that many stochastic processes have this form. Many stochastic processes have this form. So that's just an analogy from classic calculus. In usual calculus, you have differentiable functions and non-differentiable functions. Yeah, analogy with ordinary calculus. Analogy with ordinary calculus. You have differentiable functions, and you have non-differentiable functions. Obviously, there are functions such as f is equal to absolute value of x. That function is continuous but not differentiable. Yeah, that's okay. And differentiable functions there are a lot of, for example, if I write something exponent of, I don't know, cosine of x plus x squared, that will be a differentiable function, obviously. And if you understand that not all functions are differentiable, but many are differentiable, or at least non-differentiable functions may be approximated well by differentiable functions. And obviously, differentiable functions are more convenient. It's easy to, let's say, optimize something. You just calculate the derivative, make it 0. These functions are easy to work with. We have some theory how to find strema of these functions. So basically, yes, not all functions are differentiable, but differentiable functions are nice functions. Nice functions, and they can approximate bad functions in many cases. But probably you will agree with me that any function f of x, any function f of x, if it's differentiable, if the function is differentiable, then it may be written as f0 plus integral from 0 to t f prime u du. Any differentiable function can be represented by a constant plus integral. Any differentiable function is the sum of constant plus integral because it's differentiable. That's okay? Yeah, that's fine.
Why? So on the left we have x, but on the right we have from 0
sorry,
to from 0 to x.
Yeah, from 0 to t. You're right. Yeah, you're right. That's better. Okay. So continue. So basically, good functions can be written in form constant plus ordinary integral. And the idea of this notation, these are ordinary differentiable. So this part, integral from 0 to bu du, represents something from ordinary calculus. And we add some noise, some randomness inside differentiable function. We add some noise inside the function. Okay. And so we can represent in this form large number of stochastic processes, because we see basically differentiable function plus some noise. So basically, the equation xt is equal to x0 plus integral from 0 to t au d wu plus integral from 0 to t bu du means that xt is locally similar to differentiable function plus some noise similar to plus some noise proportional to Wiener process. So basically, the process xt is similar to differentiable function, some noise proportional to Wiener process. That's okay. That's the reason we need to model large number of functions, and we need to write them. But we need to write them quickly. Okay, any questions? Okay, because I don't know, you don't understand whether you just lazy to answer. Okay, so let's state some rules of manipulating stochastic intervals. First, the name, the process. So that's a definition. The process that can be represented in this form. In this form, we have discussed t is equal to x0 plus integral from 0 to t au dwu plus integral from 0 to t bu du. This process is called ETAS process. And once again, to write it quickly, we write dxt is equal to at dwt plus bt dt. Okay, let's now write theorems in two styles. Yeah, now let's write some theorems in two styles. I'm not interested in mathematical in all precise details of the theorems. I just like that you understand the difference between hand notation and full notation. Yeah. So let's state some theorems. Theorems. And let us write these theorems in short notation, and full long notation. Yeah. Honest, let's say honest notation. I'm not interested in exact mathematical assumptions. I'm interested in using shorthand notation and long notation. Okay, if here are some mild assumptions, some technical assumptions. Then expect value of at dwt is 0. What this really means. So let's write this theorem if some technical assumptions to avoid something tending to infinity. There are some technical assumptions, but that's not my goal. Under some technical assumptions, what should I write here? Expected value of what is equal to 0. What this really means. Anyone?
Integral from 0 to t au du.
Au dwu is 0. Okay. Yes. So okay, let's continue. If some technical assumptions, then variance of t dwt is expected value of at squared dt. What do we really mean? Some technical assumptions. So we mean that variance of integral from 0 to t a u d w u is expected value of integral from 0 to t a u du. That's okay? Any questions here? So that's very popular, and we need to, because to understand theorem, let's forget the technical assumptions for the moment. They're not as important as the idea of shorthand notation. Yeah. Yes, right. So that's a precise statement. Yeah, I need to specify these some technical assumptions, but let's omit them for the moment. Okay, one more theorem. If some technical assumptions and xt is equal to h of wt and t, then dxt is equal to dh dt times dt plus dh dwt times dwt plus plus 1/2 dh, the second derivative ddh to dwt squared multiplied by dt. Honest meaning. So when I write this, what do I really mean? What do I really mean? So this theorem is called Ito's lemma. Ito's lemma. What is the honest meaning of Ito's lemma? If some technical assumptions and xt is a function of wt and t, then what should I write here? Anyone? Anyone?
We should write that then x is equal to, and what we have then? We have that probably x.
x0.
So it should start with x, yes? Yes, it's equal to x0 plus integral from 0 to t.
0 to t d h du times du plus the second integral from 0 to t h dw times dwu plus 1/2 integral from 0 to t the second derivative of h with respect to dwu squared times du. We just replace everything without integrals, and we replace the upper limit of integration by t and the moment for the variable that changes, we may replace by any letter, u, s. Well, that's not important that we replace by u. That's important that t, the upper limit of integration. Yeah. Okay. Any questions? Okay, let's try to apply this example. Okay, again, I will copy it because it's very important and we will use it many times. That's tough. I understand that. Oh, we have the integrals, they are tough by themselves. Now we have some strange notation to simplify things, but when you first encounter it, it seems why we have to reduce notation. Okay, so let's solve some examples. Either xt is equal to w squared. Okay, consider the following example. A, what is the value of x0? Find dxt in short hand notation. Find dxt in shorthand notation. Find t in honest, in full, right. Okay, let's solve this step by step. Okay, do we get A? X0 is W0 is 0. Okay, A is false. Okay, B, dxt. We need to take the respect to t, but no t here. Xt is a function of wt and t, but here we have no direct. We do not encounter t directly. We encounter only wt. We do not encounter t directly in the formula. So hence is 0 times dt plus twice wt times dwt. So I just consider this one. Plus 1 over 2. The second derivative will be 2 times dt. That's shorthand notation. Now let's cover full notation. Xt is equal to x0 plus integral from 0 to t 0 du, that's the first guy, plus integral from 0 to t twice wu dwu, plus integral from 0 to t 2 times d. So I just copy the previous formula, but add integrals and then pay attention where the time is t, where the time is u. So basically, same formula but written with integrals. Yeah. Or obviously, in this case, I simplify. Yeah, that goes to 0. That guy goes to 0. So wt squared can be presented as 0 plus integral from 0 to t2 times wu dwu plus integral from 0 to t 1 times du. Yeah, and see that wt squared has this representation by sum of integrals and the constant. Okay, any questions? Yeah, let's consider some more examples. We really need to get used to this rule. Okay, one game. Example 2. Let's consider xt, that is exponent of t times w squared. That's random process. Okay. Okay. My question is, or even plus 1. Find x0 find the dxt, find the xt full form, so shorthand notation, short form, and find full. So the same question. Let's solve this exercise. What is the value of x0? What is the value of x0? X0 is equal to that's an easy question. What is the value of x0? It's n0 times 0 squared plus 1. Okay. So now let's calculate dxt. Let's copy here the ETAS formula. And let's copy here this formula. That dxt is f prime h prime with respect to t times dt plus h prime with respect to w dwt plus a1 2 h prime prime with respect to ww dt. So that's the formula we use. Its formula once again, that it is formula in short notation. So this formula doesn't make sense itself. Yeah? The right-hand side does not exist. The left-hand side does not exist. The right-hand side is not variable, but the formula is easy to remember. It looks a little bit like Taylor series. It's easy to remember, and so it's easy to quiz. Yeah. Okay, dxt in my case is equal to, okay, let's calculate. What is the derivative with respect to t? Okay, it's exponent. T is wt squared plus 1 at t plus. What is the derivative with respect to w? I have w here. I will have exponent of t minus wt dt. And add one more, 102 102 exponent of t times twice, that's the first derivative, second derivative, times dt. And then I recover the full formula. Okay, xt is 0, x0 is just 1, plus integral from 0 to t exponent of u w squared plus 1, plus let's join these two under the same umbrella, plus exponent of u du. So I join two integrals of the same kind, and I add the last integral from 0 to t exponent of u wu dwu. So that's my expression for xt. Any questions? Is it okay? That's honest. It's real object, real mathematical object. That's a random variable. We can calculate its expected value, its variance. And this is just short. Okay, let's do one more example. Let's calculate one more example. Let's consider xt, that is exponent of wt minus CO2. Let's calculate a x0. Let's calculate dxt. Let's calculate xt, represent xt as a test process. Once again, it's very easy. We need to get used to the going from shorthand notation to full form, but that's probably not that hard. We use the notation, and yeah, that's agreement. In some other world, maybe aliens, they use other notation for stochastic integrals. I don't know. Okay, what is the value of x0?
One again.
Yeah, we have exponent of 0 minus 0, 2. We have 1. Okay, what is dxt? Once again, let's write this form in shorthand notation. Dxt is h prime with respect to t plus h prime with respect to w dwt plus 1 over 2 h prime prime with respect to ww dt. Okay, so in our case, so we can replace it by exponent of w times exponent of minus t over 2. If we calculate the derivative with respect to t, it will be minus 1 over 2 times exponent wt times exponent minus t over 2 times dt plus the second term. In short form, we have no integrals, but in full form, we will recover plus in exponent wt times minus t over 2 dwt plus 1 over 2, we integrate the second time, 1 over 2 exponent wt times exponent of minus t over 2 dt. Okay, so now we have short form. So even short form is long, yeah? Even short form is long. So that's why we prefer short form, because the long form will be even big, even uglier than that. If short form is ugly, then long form will be ugly as well, even more. Okay, so xt is equal to 1, that's x0, plus integral from 0 to t. I will collect these two guys. So it will be minus 1 with 2 exponent u exponent minus u over 2 plus 1 over 2 exponent wu exponent minus u over 2 du plus integral from 0 to t exponent of w times exponent of minus u over 2 dwu. We see as well that the first integral, there are nothing inside, that's just 0. So we've got that our xt is just of 1 plus integral from 0 to t exponent of wu minus u over 2 dwu, and hence without limits, we have calculated this integral. Yeah, we have calculated this integral without limits. So integral from 0 to t exponent of wu minus u over 2 dwu is just xt minus 1, but xt is exponent of wu minus, sorry, t of minus 1. Yeah. We have one more integral. So now we know all the three integrals. Now we have already discovered three integrals. Integral 0 to t times. So our table of integrals, yeah, integration table, integration table is very big. Yeah, integral from 0 to t is dwu is wt. Integral from 0 to t w times dwu is wt squared minus t over 2, and all from 0 to t exponent of wu minus u over 2 dwu is exponent wt minus t over 2 minus 1. Yeah, our integration table is very big. We have three integrals inside. And all these integrals, they have a financial interpretation. That's if we consider this as the price process, we consider as a quantity process, then that is our net profit. Yeah, all these integrals have the following interpretation. Okay, by the way, we have calculated the second integral. We have used limits. Yeah, we have used limits. Limits 1 week ago. We calculate these limits 1 week ago. Okay, let's calculate these integrals quickly without limits. Now we have a powerful tool, that is Ita's lemma. Once again, that's called Ita's lemma. And we have this powerful tool and calculate many things very quickly. Let's see what we can do now with it. For example, we have discovered this. Yeah, using this lemma, we discovered this. Hence, we can say that wt squared, that's twice integral from 0 to t wu dwu. This integral is very easy. That's an ordinary our old friend. Our old friend is equal to t, and hence integral from 0 to t wu dwu is equal to wt squared minus t over 2. And once again, we have new rules of integration, and we are most ready to work with some more realistic models for price, and because obviously WT is a bad model for a price. It can be negative, yeah, and it seems like a toy for the moment, but now we have this. We have some theorems. Yeah, we have created 3 theorems, but these theorems are very powerful. For example, let's calculate something using these theorems. Okay, we have this. For example, let's calculate question 1. Okay. Let's calculate what shall we? Okay, let's calculate expected value of exponent of WT. For example, let's calculate expected value of exponent of WT. The question has nothing to do with integrals. No integrals, no calculus, at first sight, but okay, there are many solutions, and just integrate from minus infinity to plus infinity exponent of w times PDF of ut ww. Yeah, that's the first strategy. Yeah, the first strategy. It's a possible strategy, but you need to integrate. And I will calculate this expected value without any integrals. Or more precise, I will not integrate. I will use properties integrals. Okay, I know that, for example, look back at my integration table. I know that I have an expression like this. Yeah, I have an expression like this. Yeah. Let's get solution with new technique. Solution with new technique. We have integral from 0 to t exponent of wu minus u over 2 dwu equals exponent of wt minus u over 2 minus 1. Okay. But we have some theorem. Let's recall we stated these theorems. One theorem states, under some technical assumptions, we will not go into details. We will believe that they are satisfied for an exponential function. At the moment, we'll just ignore what these technical assumptions are. They are really that something exists. So to avoid something non-existence, processes that block to infinity, but that in finite time. Okay, this expression is 0. The expected value of stochastic integral is 0. I'm happy. If something is a stochastic integral, then I can calculate the expected value of this thing. And in calculations, it's 0. That's very powerful weapon. Yeah, that's very easy to calculate. Okay, let's go back to our example. Calculate expected value for both sides. Let's calculate expected value for both sides. This expected value is 0 by theorem. The expected value is 0. So if I can represent something as a stochastic integral, that simplifies greatly the calculation of expected values. Yeah. Hence, expected value of exponent wt minus squared minus 1, 0. Hence, expected value of exponent of wt multiplied by exponent of minus t over 2 is equal to 1. Hence, expected value of exponent of wt is exponent of t over 2, and I'm happy. I have solved problem. In this original text, there are no stochastic integrals at all. But I know that stochastic integrals, they have very wonderful properties. They are easy to manipulate, and they have expected value 0. And this brings me a new tool to calculate expected value. I represent something, stochastic integral, something else. Yeah, obviously not all processes can be represented as one integral. Maybe I need 2 integrals. But if I have this representation, that's need to solve the exercise. I represent thing by stochastic integral. Expected value of stochastic integral is 0, hence, the problem solved. No real integration was used, the properties of integral. Okay, I think that's all for today. If you have questions, then don't be shy. But basically today, we have discussed that we have continued our discussion of stochastic integrals. Yeah, stochastic integrals, they represent net profit. And we have established some rules. Sorry, we have not established, we have stated. We have stated 3 properties. One property is how to go from one process. So this property is very useful. It is lemma. It says how to go from one process to another. If you know something about process S and process YT that is linked to XT, so you know something in YT. Useful, you can go from one process to other process. And 2 properties, how to calculate expected value and how to calculate mass. And that's great. So we have stated these 3 properties, and once again, I should pay your attention that in many textbooks, it's common to use strange notation that has no meaning itself, but it great saves time and space, and we will also use this notation, but we will always state that this object does not exist. We really mean something else when we write that expected value of AT/dW0. We really mean that the expected value of stochastic integral is. Okay, thank you very much. If there are any questions, don't be shy. Okay, that's all for today. See you next time.
Thank you. Goodbye.